All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are actually doing a bit of an earlier stream, but like not too early. It's maybe 3 hours earlier, 2.5 hours earlier than when I usually end up starting the stream. I actually wanted to start the stream an hour before this as well, but my time management skills are horrible, and so that didn't happen. But this does make it so I don't have to do one of the quieter streams today. That's why I started the stream earlier, so I wouldn't have to do one of the quieter streams. Why? Because reasons. Okay, so between yesterday's and today's stream, I've made a bunch of progress. I've done a bunch of things. I was looking into the index file and I was trying to understand what the staging area is. I had a bit of a confusion about what the staging area is. And I had this idea that the staging area always represents the working directory. That is true, but also not true. That's the wrong way to look at it, and that's what I discovered as I was reading up more on, or well, chatting with Gemini more about the staging area. Basically, the staging area holds the staged changes. So what does this mean? Now, it helps to imagine three different, actually not even imagine, like the like in terms of our Git repo, we have three different things that are at work. One is your working directory. That is usually a representation of the latest snapshot. Um, that's your working directory. That's where all of your files and directories and stuff are. Then you have the Git repository, the Git database. This is where your all of your commits and blobs and trees and so on are stored. And then you have the staging area. I don't know if I actually, I'm pretty sure I didn't list those out in the right order. But don't worry about the order. Then you have the staging area. The staging area. This is an interesting concept because so what happens is and I can actually demonstrate this. Hold on. Let me come here. Um, I think it was, wait, um, here. The way that I'll demonstrate this is by doing this. So right now, if we look at, oh, wait, I need to commit this change. So this would be the ninth commit. I'll make another commit. Um, Hold on. Wait, what? Oh yeah, I cleared this. So at this point in time, we don't have any unstaged changes, right? The state of our index file, or rather, I should say, the index file represents the state of our working directory right now. But the reason for that is because we are the working directory is representing the latest snapshot. That's how this is working. In our latest snapshot, this is what the hashes of each of the files look look like. Okay, you don't have to look at like all of the details, all you don't have to look at the entire long hash, but pay attention to the first like 7 or 8 characters or 6 or 7 characters um, of each of the hashes. And more specifically, because I'm only going to be making a change in sum o2, so more specifically only look at that hash. Sum o2's hash is the first, let's say, 7 characters are D15BB 377. Is that 7 characters? Yeah, that's the hash, right? And we can further um, we can do actually if I how much data is in this file? Oh, there's a lot of data here. Though I mainly want to show you the ending, right? Um, well, okay, I don't need to show you the data of the file. Just understand that in our latest snapshot, that that hash D15 BB377, it represents. Hold on, is that eight? I, s- I think I read that wrong. It's D15 BB377. Okay, that's seven. That's not seven. D15. That's eight. Oh, that's eight characters. Either way, doesn't matter. Just that's the hash. Sorry, I got hung up on that. Um, that's the hash as of right now. So the index file stores the staging area. It represents the staging area. The staging area currently, because we haven't staged any new changes, the staging area represents the latest snapshot, which is basically the the current state, which is also the current state of our working directory. The staging area, you can say it represents the current state of the working directory, which is basically whatever the snapshot, the latest snapshot says, right? Okay. Now, um, I'm using git ls files s to read the staging area, and that's how I'm getting this data. Now I'm going to make a change here. I'm going to say this is yet another sentence. Okay, I'll save this change. You can see now that there's unstaged changes. So I'll stage that change. I'm not going to commit this. I've just staged the change. Watch what happens when I list out um, the staged files now. Specifically, pay attention to sum02, the hash of sum02, and compare it to the hash that you saw previously. Um, just to, write it out. The previous hash was D15BB37, and the current hash is, wait, let's do this. And the current hash is 041E59. Is that 7? 595 there. So now the hash has changed. And keep in mind, git ls files s is reading the staging area. So these are our staged changes. This is what the index file does. This is what the staging area does. So the staging area doesn't, um, like, in a way, you can say that it represents the current working directory, but more specifically, a more I'm not sure how to put that into words, but a better way to look at that would be, um, it holds the changes that haven't been committed yet. It's less about representing the current state and more about holding the changes that haven't been committed yet. Because I guess if we said that it represents the current state of the directory, technically it's right. However, kind of not exactly. That's not the point. Representing the current state isn't the goal. The goal is to store the change that has happened, the change that has not been staged. Sorry, that has not been committed yet. And uh, so then I was wondering, okay, then why do we even have a staging area if the working directory doesn't like what's the idea there? The idea is this: now that I've staged this change, right? I can decide if I want a specific change to go. Oh, actually, sorry, hold on. Let me restart that example. Let's say we have our working directory in a specific state, right? And we want to make two changes, or we want to make a change. I'm actually gonna just reiterate um, the example that Gemini gave me. Let's say we want to make a change. We want to push a change. We want to commit a change. However, we discover that there's a typo in somewhere in, you know a file. Now we can either fix the typo and the change and then commit all of that together, or we can fix the typo first, and then like stage that, but then not stage the other change that we were actually planning on making, and then we can commit this typo fix first. This is one of the uses. It separates the actual staging, if that makes sense. Like, you can decide which changes you want to stage, and within the staging area we're going to hold these changes, and then these changes can be committed. You can also this in this way decide which changes you don't want to commit yet. So this way you can separate changes into multiple commits, and that's one of the multiple use cases where the staging area can be useful. However, all that being said, now I understand. Actually, why did I say however? That being said, um, now I understand what the index file is for and what the staging area does exactly. It's not exactly a representation of our staging area. It's a representation of our staging area when we have, sorry, what exactly the staging area does. It's not a representation of the working directory. It is a representation of the working directory when we haven't made any changes yet, or when we haven't staged any changes yet. Then it is a representation of our working directory. But once we have made some changes and staged those changes, then it's not necessarily going to be a representation of the working directory. Sorry, I confuse these two things because I'm trying to explain a scenario where where the staging area would be used, but then I keep confusing it. So if we have our working directory and we have the staging area, initially they're both going to match up when you haven't made any changes. Then, when you make a change in your working directory, the change hasn't been staged, so that's not going to be recorded, right? If you look at the hash at that point, the hashes in the staging area would be represent they would be a representation of the latest commit, not a representation of your current working directory state. Once you stage those changes, then the staging area is a representation of the current working directory. But it's and this is why I had to learn and understand that it's wrong to connect the working directory with the staging area and be like, oh, the staging area always represents the working directory, because that's not true. These are two different things. The working directory is where you're doing your work and you're going to make your changes. The staging area, initially, when you have not made any changes since the latest commit, then the staging area is going to match the working directory, but more specifically, it's matching the latest commit. And it just so happens that your working directory, it matches the latest commit, right? Once you've made a change, then your working directory and staging area, they don't match anymore. The staging directory is the staging area is not a representation of the working directory anymore. It's now a representation of your latest commit. You need to stage the change that you just made. Once you stage the change, now the working directory and the staging area, they both could match, but there's a caveat there as well, or there's a little not a caveat, but like it kind of depends. Because, like, let's say you have two changes, but you only staged one of those changes, right? So now the staging area has that one change, but it doesn't have all of the changes from all of the unstaged changes from the working directory. So now the working directory, the staging area, and the latest commit all are in different states. So that's kind of why these things are useful. That's why having them as separate, it's in a way, I guess you can call it a separation of concerns. I guess that would be one way to look at it. But yeah, it took me some time to understand this, and I'm glad that I understand it now. The next thing I was doing is reading up on the concept of file descriptors, file streams, and named pipes, because I've understood the concept of named pipes to a certain extent, more specifically named pipes in Linux. I haven't played around with named pipes on Windows. I do think they have named pipes or something named, because I remember there being a thing where you could like have, so there's named pipes, and there's also memory mapped um, IO or memory mapped files or something like that. That's another concept I should look into, actually. That is definitely another concept I should look into, because I believe that is also a way that we can use to have um, what is it called, IPC, inter process communication. And this is great, dude, because a couple years ago when I started looking into how I can make multiple different programs talk to each other, the only thing I knew about, because I mean I was still very new to this concept, the first thing that I started with was sockets. That's what a lot of people were recommending, and sockets uses networking. So it's not necessarily something going out of your computer, but it's using the networking related concepts in order to do that. You create a socket, bind the socket to a certain port. The address doesn't matter because it's on the same computer, and then you can have multiple. You can have one program sending data to the socket and another program reading data from the socket, right? That's a on a very high level. That's how um, you would that's how you would use sockets for IPC. But in addition to sockets, you also have named pipes and memory mapped files. I've not looked into memory mapped files too much, and I'm now exploring named pipes. Named pipes are a very interesting concept because, at least from what I understand, and at least on the Linux side, they're essentially buffers. Um, you can store data in them, and they're accessible as regular files. So they're given a path. Like for example, if I did something like echo ABC. Oh, let's do this, and I want to print out this thing specifically. So what this is doing is this is something called process substitution. This stores the data. This runs the command, and the command is going to have an output. The output gets stored into a named pipe which is accessible at that location, slash dev slash fd slash 63. The amazing thing about process substitution is that the OS handles, or maybe it's the shell specifically, that the shell handles whatever is handling. I need to look into what exactly is handling this. I think it's a mixture of the shell and the OS. But yeah, the amazing thing about process substitution is that a named pipe is created, and the data is passed into, well, I was using echo, right? So um, the data is passed, or that file is passed into echo, so echo can then read that, and immediately the thing gets deleted as well. So the shell or the OS is handling the management of this thing. So I could do something like what is a good what is a good oh wait, so we could do, let's do ESA. Okay, ESA tree. This is gonna be very long. Hold on. I'm trying to create a good example here. How do I create a good example here, dude? Because like I had good examples. I had good examples. Like for example, reading from a file, reading from two files, and then diffing them. Um, oh, you know what? Yeah, we could do that. So let's do diff u. I'd run this example yesterday. Oh wait, no, that is that command substitution or no? Command substitution pastes the output directly here. Process substitution pastes the output into a named pipe buffer, and then it returns the path to that buffer, so you can then read from that path. Yeah. Okay. So let's say git uh, ls tree, I guess. Yeah, ls tree head, and then git ls tree head -1. So we have a diff here. Now, what has happened here? Oh, actually, this is great because if we look at the top of the output there, you can see two different named pipes were created. One was 6.3 and one was 6.2. If I try to read either of these named pipes now, let's see what happens. It says there's no such file in the directory. So the thing was created, used, and then deleted as well. So again, I don't know if it's the shell or the actually let me ask Gemini so I can give accurate information. Hey, when I use so and so, when I use process substitution using this, what exactly is handling? Actually, I think it would be a mixture of the two because it might be the shell that's initiating the creation of the pipe, but then it's the OS and the kernel, more specifically the kernel, that would be responsible for actually creating the pipe, right? And then later on, also when the pipe has to be deleted, it's the OS/kernel that's going to be responsible for deleting it and freeing it up. The shell just initiates that operation. Okay, what exactly is handling um, the management of the pipe? Is it the shell or the OS/kernel, or is it that the shell uh, initiates the operation and the OS/kernel does the operation? Okay, you've hit on a fantastic distinction. The short answer is it's a beautifully coordinated team effort. The shell acts as the architect and supervisor, while the OS/kernel does the heavy lifting for creating and managing the actual data pipeline. Okay, the shell's job, the architect, the shell, like Bash or Zish, are is is entirely responsible for parsing the syntax, setting up the environment, and orchestrating the processes. It doesn't actually handle data transmission, but it sets the stage. Parsing. The shell uses so and so syntax, process substitution syntax, and knows it needs to connect the output of CMD2 into the input of CMD1. Requesting the pipe. The shell asks the OS kernel to create a temporary pipe. Then the shell forks itself to create child processes for both CMD1 and CMD2, and then rewriting the command. This is the clever part. The shell replaces the entire CMD2 string in your command line with with a file path that points to the pipe and kernel. Wait, what? That points to the pipe the kernel just created. Okay. On Linux, it usually rewrites it to something like so and so. Okay. Execution. Finally, it tells the kernel to execute. All right. Give me a second here. I just remembered that I forgot to. Oh, wait, there's something else that I forgot as well. Okay, all right. Yeah, sorry. Oh, yeah, sorry. I was just looking at something. Let me open up my chat on my phone. Um, for some reason, this thing is not showing me as live. Am I not live? No, I'm live. It was just a uh Twitch mobile app bugging out. Okay, all right. Okay, then the OS slash kernel's job. The kernel manages the hardware, memory, and actual data flow. The shell has no idea how bytes move from one process to another. It just tells the kernel to make it happen. You know, this might be like an incredibly limited project, depending on like how I go about doing things. But at some point in time, I do want to try creating my own system. What kind of system, I'm not really sure, but like something resembling an OS running on hardware. That's the best way I can describe it. I want to create something resembling an OS running on hardware. Um, the thing is, I'm going to be making the hardware myself, and I'm also going to be writing, the kernel myself. There's not going to be an OS like on top of, well, I guess you can call it an OS, but like it's going to be a kernel, and there's going to be a shell, and you'll be able to do stuff in it. I feel like it would be an interesting concept. What I want to do is first I want to create the hardware myself. I don't want it to just be a microcontroller. That's the thing. I don't just want the thing to be limited to a microcontroller. What I want to do is try and make the system modular in a way. So one ESP32 would serve as a processor, and I'll take heavy inspiration from current hardware or past PC hardware, where you have a processor, you have RAM, you have some sort of bus controller that routes data from one hardware to another or stuff like that. Additionally, we can have stuff like a display driver, maybe something that kind of serves as a GPU, something that can be programmed as a GPU. Um, what else? What else? I'll have to look into like the various all the different possibilities there. It should be an interesting experiment. I don't really want to create a one-to-one computer copy, but I want to try creating something. Like, okay, we won't have like one motherboard. I don't think that's necessarily gonna I don't think that's necessarily gonna work out. I'm gonna have to have multiple different things. So um there's gonna be a processor, then there's gonna be RAM. I think I'll have a separate controller for the RAM. There's gonna be um storage. I think I'll have a separate controller for the storage as well. I feel like that's the best way that I'll be able to set this up, by having multiple different controllers for each of the tasks. I don't think um one machine handling all of that would really work out that well, because each of them has to do its own processing, right? I feel like the power requirements there would end up being high. I'll have to sit down and think about it because, like, yeah, how would that work? Let me ask Gemini. So okay, yeah, I think I'm done with this conversation about, the shell slash OS slash kernel. Okay, hey, so I do ESP32 projects use um, using no STD Rust, but that's not really relevant to the convo. Well, okay, yeah, I can just mention it. Using no STD Rust, um, as a bit of a pet project, I had this idea to create something resembling the concept of a kernel, or let's say OS slash kernel, running on hardware. The thing is, I want to design both the kernel, or I want to build both the kernel and the quote unquote hardware it's going to be running on. I want something similar to a computer, or at least I'm deriving inspiration from computer hardware architecture, and I plan, yeah, okay, keeping that in mind. So far, the idea I have is to have one ESP32 as a processor, another as a memory controller, another as a storage controller. I spelled storage wrong. Storage controller, etc. I haven't. Oh, wait. Oh, yeah. I might also need a bus controller to route data to various hardware. I haven't looked too deep into older computer hardware architecture, so I would like you to give me some info on that, and also um, let me know what you think about my idea and what you would suggest as well. Because I looked into computer hardware architecture a while back, and it's like it is, believe me when I tell you, it's its own world basically. Computer hardware on the lower level, the way these things work, it is nothing like stuff going on the higher level. When you are using anything on the OS level, when you are using stuff on the OS level, the whole idea is for all of the hardware related stuff to be abstracted away. So you don't have to worry about how those things are working. You can still learn about them, but the idea is for them to be abstracted away so you can just use the computer as it is. So, like stuff going on the hardware level, it is its own separate world. Designing the hardware, programming that hardware, these are like completely like this is its own separate thing. This is very, very low level programming and also hardware design, which hardware design itself is inherently low level. So, kind of redundant to say low level there, but yeah, this is its own separate world. It's nothing like the stuff that you do on the higher level, on the OS level. Even when you're doing low level stuff on the OS level, it's nothing close to, the hardware. And that's by design. You're not supposed to have to worry about stuff on the low level. And in this day and age, a lot of times, especially if you're using languages like Rust, for example, um, the idea is to make things even more abstracted, so that you are able to write your program in one language and target multiple different types of hardware, different platforms, different OSs, um, different processor architectures, and so on. All right, okay. Gemini replied. Gemini said, "This is an incredibly ambitious and deeply cool pet project, building both a custom quote unquote hardware ecosystem and a no STD Rust kernel to run on it. To run on it is the ultimate way to truly understand how computers work under the hood. Using multiple ESP32s to simulate distinct hardware components like the CPU, memory controller, storage controller is a brilliant way to bypass the massive hurdle of custom PCB routing and high frequency hardware design, while still forcing you to solve the exact same architectural problems that engineers faced in the 70s, 80s, and 90s." I actually think, yeah, I'm going to be going back to around that time, because like what I'm doing is not going to be anything close to what hardware is today. In fact, what I'm going to be building is probably going to be even more primitive than what they had in the um, 70s, 80s, and 90s. But it's going to be something on that level. I was kind of expecting that, anyways. Okay, here's a breakdown of how older computer architectures handle this, a critique of your proposed setup, and some concrete suggestions to make this work smoothly. How older hardware handled, I think Gemini is focusing on older because I mentioned the word older. Yeah, I think that's why. Anyways, okay. How older hardware handled this? The chipset era. Wait, we don't do chipsets anymore? Okay, I didn't know that. Okay, all right. In classic computer architecture like the 8086, um, 68,000, I've never heard of that one, or early Pentiums, the CPU didn't talk directly to everything. It used a system bus, address data and control lines to talk to a chipset. Eventually, this evolved into a standard two-chip layout. The North Bridge, I remember that. I remember that. Okay, the North Bridge, which was the memory controller, this sat directly on the fast system bus with the CPU. Its sole job was to route data between the CPU and the high speed system RAM, and it had to be fast. Then the South Bridge, which is the I/O controller, this connected to. Sorry, I lost where I was reading. Okay, found it. Um, this connected to the North Bridge via a slower bus. It handled the slow things such as hard drives, keyboards, serial ports, and expansion ports. Okay, all right. Oh yeah, there's the fact that the computer, quote unquote, computer here would also need to be programmable, right? Yeah, I didn't think about that. Okay, all right, all right. In your setup, the CPU ESP32 will mimic the processor, while your other ESP32s will essentially act as these dedicated bridge controllers. Evaluating your idea, the communication bottleneck. The biggest challenge in your project isn't going to be the Rust kernel, it's going to be the inter-integrated circuit, or rather inter-ESP32 communication. A real physical CPU, a real physical CPU bus has dozens of parallel pins, so it can transmit a 32-bit memory address and 32 bits of data simultaneously in a single clock cycle. If you, oh, I didn't think about that. Okay, hold on. If one thing is gonna be, I didn't, oh shit, dude, I didn't think about that. If one thing is gonna be the processor, I need to actually design the processor. As in, the processor has to be able to execute instructions. So I'm gonna have to come up with my own instruction set architecture. Yeah, dude, I didn't think about that. Okay, okay. It's still a doable project for sure. Like I would then be writing firmware for the memory controller. I would be writing separate firmware for the I/O controller, which now I'm realizing is gonna include the storage and other things like input, possibly output as well, right? Though for the output, I kind of want a display controller. So there's going to be multiple different controllers going on here. This could be an interesting concept. This could be an interesting, yeah, this could be an interesting concept, dude. It's probably going to be limited to 32 bits though. That's one of the things. Um, oh, you know what I could do? You know what I could do? I want this to be I want this to be Rust focused specifically. Hey, so I do. Wait, I'm writing a new prompt to Gemini. Hey, so I do ESP32 projects using NoSTD Rust. I'm wondering, has anyone um, made quote unquote firmware to turn an ESP32 into a 32-bit processor? Because if someone has already created this, I could probably just use their own design instead of having to, like, come up with my own design. Because holy shit, dude, designing the processor, designing an instruction set architecture, it's going to be a lot of work. And that's going to be a lot of low level work. That's going to then take time away from slightly higher level work that I could be doing. Like I could be programming the firmware for the South Bridge, South Bridge, or the North Bridge. But instead, I'm going to be stuck building the processor architecture myself. Which, don't get me wrong, it would be pretty rewarding in its own right. But then it's going to take time away from other stuff. Okay, it sounds like there might be a slight mix-up in terminology. But the great news is you don't need any special firmware to do this. Your ESP32. Okay, yeah, I had a feeling that Gemini would be confused. Sorry, I should have been more clear. Has anyone created their own custom ISA and implemented it using an ESP32? Okay, designing a custom instruction set architecture and building software to process it is an awesome rabbit hole to fall down. While you can't configure the physical hardware logic of the ESP32 to change its native instruction set architecture, since it's an ASIC and not an FPGA, people absolutely do this through software emulation and interpretation. And doing it in no STD Rust is an increasingly popular way to build fantasy consoles or secure runtime environments. If you want, dude, hold on. What if someone has made a 32-bit, hold on. What if someone has made their own 32-bit um, emulated CPU. And this is the important part. It has to be 32-bit. It has to be no STD rust, right? But as long as it's no STD rust, would I then be able? Oh, it should also be. I guess it should also be targeting embedded HAL. I I think so. But yeah, if that is the case, would I be able to? No, let's forget about embedded HAL. Holy shit! Let's forget about embedded HAL for a second. Sorry, zoned out. Okay, let's forget about embedded HAL for a second. What if someone has made their own 32-bit? Yeah, let me look that up. 32-bit CPU, Rust, no STD. Okay, I just saw a post. I haven't read the post yet, but this is what they mentioned. They said, I built a 34321 file. Oh, do they mean a 34,321 file, no STD bare metal kernel in Rust? Okay, they're saying that they built a bare metal kernel. Now, this got me wondering, do I really need do I really need to create a separate CPU? Why am I creating a new ISA on top of what's already a CPU? Why not just design the kernel or build the kernel directly on top of the existing CPU? That makes sense, right? Like, but then, oh, yeah, no, I just realized the reason I'm doing that is because how are we giving instructions to this computer? Oh, why am I trying to give separate instructions to the computer? I think I need to sit down and think about what exactly I'm doing here. Yeah, because we have so each of these are processors, right? The controllers are all going to be their own individual processors. Um, dude, I wish I had taken the time to learn DirDraw so I could have quickly switched to like a DirDraw screen and drawn stuff, and it would be even more easier to do it now, especially since I have the ability to do like a zoom kind of thing. But yeah, okay. What was I saying? Yeah, so we're gonna have the ESP32 as a processor. We're gonna have a processor for, or we're gonna have an ESP32 for each of the different components, right? But each of these ESP32s is a processor that's able to run firmware on it. So for the controllers, I have the firmware, right? For the processor itself, the ESP32 that's meant to be the processor, how am I going about this? Because I don't want to be programming stuff. Like even if I make my own instruction set architecture, I don't want to be limited to just programming stuff with with assembly. Like as great as that might be, I don't want to be limited to just that. I actually want to use Rust. But then if I create my own instruction set architecture, I'll have to create my own way to, you know, compile Rust code down to that architecture. And while that would be an interesting um it would be an interesting thing to study. It would be a very educational thing. I feel like it's also going to take a lot of time and effort, and that is time and effort that I would be taking away from deep learning and robotics and basically everything else that I want to do. I don't want to do that, dude. No, no, no. Okay. Uh, hold on. There has to be a different way. What I could do is, so I could build a modular system, and I could build a library, a Rust library. This will allow me to remain within Rust. So that's a good thing. I could make the library embedded HAL compatible, and the how would the program be loaded though? That's the thing. I need to find a way, because if the program becomes so long that it doesn't fit into the ESP32's memory, which I'm pretty sure is going to happen at some point in time. But if the program becomes long enough that it doesn't fit, hold on. Let me ask Gemini this question. Hey, so I do ESP32 projects using NoSTD Rust. I'm aware that the ESP32 has limited memory to hold code. But this has me curious. Hold on, curious about just how long would my code need to be before I need to worry about it not fitting in the ESP32 uh, anymore. Okay, it's awesome that you're doing no STD Rust on the ESP32. Writing bare metal Rust gives you incredible control, and you're already starting from a massive advantage. No STD binaries are famously lightweight because you drop the overhead of the standard library, which is allocations, panic handling, machinery, panic handling machinery, threads, etc. But to answer your question, how long does the code have to be before you hit a wall? The short answer is immensely long. If you are writing pure code, you will likely never run out of space if you start embedding large assets like images or web pages. Wait, hold on. Let me read that again. If you're writing pure code, you will likely never run out of space. If you start embedding large assets like images or web pages, that's a different story. You know what? Images and web pages can be loaded separately, and I can actually write the code to do that loading, so that shouldn't be a problem. It'll only be a problem if the thing that I'm trying to load right now currently becomes so big that one specific ESP32 is just not able to handle it anymore. Um, then it would be a problem. But otherwise, I think we should be good. This should be an interesting project. Okay, now I'm gonna go back to wait, no. Gemini was continuing here. Flash memory versus RAM. The crucial distinction. When you worry about code, quote unquote, fitting, we need to look at flash memory, not internal RAM. Your code lives in flash. On almost all ESP32 boards, the microcontroller is paired with an external SPI flash chip, usually 4 megabytes or 8 megabytes. Um, exit. By the way, speaking of flash chips, I found out that there are a bunch of these flash chips which I can buy like super cheap. So if I ever need to create, and I feel like that's going to be um, needed when I'm creating my own RAM. I should look into like how I would go about creating my own RAM because the flash chips are meant for storage, not for well, RAM is volatile memory, right? It's not supposed to store stuff infinitely. It's supposed to just hold things there. So I should look into RAM hardware. Like what would I be needing there? Like for example, for storage, I would most likely be using an SD card module along with an SD card, of course, and the data is going to be stored on the SD card. I'm not going to have like a dedicated hard drive. And just with the SD card alone, I should have a decent amount of space. One problem with SD cards is uh, there's a chance that the data could get corrupted. So I'll need to look into ways to mitigate that. But other than that, an SD card should be fine, and along with an SD card controller. Um, I need to look into hardware that I could use to wait. Wouldn't that just be like um, a whole bunch of logic gates? Wouldn't I just be putting together a whole bunch of logic gates to create something like that? I'm pretty sure there'll be RAM modules that I can buy that as long as because with RAM, it's like especially if I'm trying to do, bitwise stuff, if I'm trying to um store the data as binary digits, it or as binary bits. Sorry, if I'm trying to store the data as bytes, then all I would need is something that can handle 8-bit 8-bit data. Wait, let me open up another conversation and ask Gemini another question. Hey, I do wait, I don't want to keep typing that out. Hey, so I do so and so. Okay. Um I'm curious that if I were designing um my own system using an ESP32 and I wanted something that resembles RAM in that um, it can be used to store data as long as there's power, um, not necessarily used to extend the ESP32's RAM. What are my options? Okay, that is a niche and deeply satisfying intersection of hardware. No, all right, fine, great. If you're looking for an external chip to store arbitrary data dynamically, as long as the system is powered, without necessarily mapping it to the ESP32's internal memory map as data RAM, you have some great hardware options. Since you aren't trying to expand the native heap via PSRAM, you don't have to worry about the ESP32 strict RAM slash MMU alignment rules. Instead, you can treat this as pseudo RAM. Um, you can treat this pseudo RAM as an external peripheral communicated with over a standard bus. Okay, so the first option is SPI SRAM, serial RAM. This is exactly what you're describing. It operates just like standard RAM, but communicates over an SPI bus. How it works, you send a read or write command over SPI followed by a memory address, then stream your data. Volatility, it's volatile, loses data as soon as power is cut. Speed is moderate to high. Standard SPI can easily do 20 plus megahertz, and if your ESP32 supports dual or quad SPI for your specific chip, you can move data incredibly fast. Okay, all right. The next one is FRAM, ferroelectric RAM. If you want something that acts like RAM, infinite write endurance, fast write speeds, but has the added bonus of keeping data when the power cuts. FRAM is the gold standard. Oh, okay. Okay, it bridges the gap between RAM and Flash. Unlike Flash or EEPROM, which require a slow page write cycle and have limited lifespans, FRAM writes at bus speeds instantly and lasts for trillions of write cycles. Okay, I have a feeling that this might also be a little expensive. I'm not sure. Okay, then there's non-volatile storage, which is emulation via external SPI flash. If you just want a place to dump data logs or configuration structs, using a standard dirt cheap SPI flash chip is the industry norm. However, no, how it writes. You write data to sectors. However, Flash requires you to erase a whole sector, usually 4 KB, before you can overwrite data. And it's non-volatile. And why it might not fit, it doesn't truly resemble RAM because you can't just randomly overwrite a single byte infinitely. You will wear the silicone out if you hammer it continuously. So then it doesn't work for me. So what I want is SPI SRAM. So let's look up SPI SRAM module. I just want to get an idea of what the price would be like. Okay, this is not what I was looking for. Uh, this is showing me actual computer RAM, and that is not what I was looking for. Oh, hold on. SPIS RAM module. Let me search that properly. All right. Okay. I'm seeing a couple here. Wait. Hey, I like the SPI SRAM idea. Could you suggest a couple of chips or modules? Okay, okay. The chips. 23LC 1024. Is 1024 1 KB? Oh, 128 KB. Okay, 1 megabit, 128 KB. You know what? Let's look that up. There is also there's a battery backed variant which is non-volatile. Let me look at the price though. If I just go for the dip chip, which honestly that's all I need, just the just the dip chip or the dip IC. I'm not sure what this is. It says PCF8574P. Let's look that up. PCF8574P. Says remote 8-bit expander for I2C bus. Right, that's not what I'm looking for. Okay, okay. You know what? I'll look this up later on. For now, I need to continue the conversation with Gemini um about the memory. No, about the computer itself that I was planning on designing. Uh, okay. Has anyone created their own instruction set architecture? Yeah, okay. You know what? I don't think I need to worry about a separate instruction set architecture. That being said, um, Okay, so as I was reading up more, I realized that I don't really have a reason to create a separate ISA or a custom CPU. Um, I could, no, what I'm really looking to do, I guess, is um, program. But then we wouldn't have a kernel, right? That would be, yeah, we wouldn't have a kernel because the whole idea is that the kernel. How am I trying to go about this? Because I could design the kernel to be like tightly coupled with the ESP32, right? And then programs can be written to run on the kernel. Yeah, yeah, right? They can be written to run on the kernel. But the thing is, if you are running something on the kernel, like what's the I would need to understand the sorry, I'm not making sense because I'm trying to think of trying to think about this. Um wait, what I'm really looking to do, I guess, is program the ESP32 to run a quote unquote kernel uh on top of it, and then also program um the separate controllers with their own firmware, and then load and run programs from. But see, that's the thing, right? It's the thing about loading and running. When you talk about loading and running, you're loading you're loading you're loading instructions, you're loading CPU instructions that are going to be executed by, well, the CPU, by a CPU. Yeah, dude. Um, no, no, no. I need to sit down and think about this. And then load and run programs from storage into RAM, and then uh, execute them using the various hardware components. The issue is I'm realizing that, no, I'm also realizing that when you have the concept of loading into RAM and running, you're basically talking about um, a separate CPU architecture, which in this case would actually be a separate ISA running on top of the ESP32. See, okay, something else I could do is I could make the kernel would be responsible for the hardware that is no, but then we run into that same issue again, right? The kernel is an intelligent system that I would be designing that would run these programs that would actually no, the kernel is supposed to handle hardware scheduling. No, dude, I need to sit down and think about this. Okay, let's see what Gemini has responded with. You've hit on one of the deepest and most fascinating realizations in computer science. You are 100% correct. The moment you want to load a file from storage into RAM and say, quote unquote, execute this, you have to answer the question, what language are those bytes written in? If you want to use the ESP32's native brain to execute that code, things get incredibly complicated because of how modern microcontrollers protect themselves. However, you aren't completely trapped into a custom ISA emulator. Let's break down exactly why this happens, the two paths you can take from here, and how you can still achieve your dream of a multi chip computer. The core problem, why microcontrollers aren't like PCs. On a standard PC, the CPU treats RAM as a playground. A program is loaded from the SSD into RAM. The CPU points its instruction pointer to that RAM address, and it starts executing. This is called von Neumann architecture. Okay, most microcontrollers, including the ESP32, use a Harvard architecture or a modified version of it. You have instruction memory where the code lives. On the ESP32, this is usually its internal flash memory, and then you have data memory, which is where variables live. Sorry, variables, stacks, and heaps live, which is your RAM. Okay, the RAM and the flash memory are different. Okay. By default, the ESP32 cannot execute code directly out of normal DRAM or external SPI RAM. It physically blocks it for security and hardware layout reasons. If you point the ESP32's program counter to a random buffer in RAM containing native ESP32 instructions, it'll throw a hardware panic. So the first path is the native route, ELF loading and dynamic linking. If you absolutely want to avoid a custom ISA and want the CPU ESP32 to run native code fetched from your memory controller ESP32. Okay, yeah, fetched from your memory controller ESP32. It is technically possible, but it requires advanced systems programming. Instead of just loading raw bytes, your kernel would need to implement an ELF loader. Okay, the app, you compile a separate Rust program targeting the native ESP32 architecture. Loading, your storage controller reads this ELF file, passes it to the memory controller, and the CPU reads it. The trick, to execute it, the kernel must use specific hardware features of the ESP32 to map the external so-and-so. The verdict, this is incredibly difficult in a no STD environment from scratch. You would essentially be writing low-level memory mapping drivers using reserved, usually reserved for operating systems like Linux or free RTOS. Then path two is the hobbyist OS route, which is WebAssembly or bytecode. Okay, okay. This is how almost all custom microcontroller OS projects handle running external programs. So basically, we introduce a holy shit. I didn't think about that, dude. We are essentially doing IR in a way. Yeah, we are essentially doing IR. So then there has to be something that runs directly on. There has to be something that runs. There has to be some sort of runtime that's executing this this stuff, right? These instructions. I need to look into that. WebAssembly is a way, but I didn't know that WebAssembly is possible on ESP32. Hold on. WebAssembly ESP32. Ultra fast WASM 3 interpreter brings WebAssembly to so and so. Yeah, okay, okay. If I and this is basically what I was looking for then, right? Not necessarily an architecture, not necessarily a separate ISA, but um but it is something that runs a separate program. So whatever program I'm writing, I could create like my own library that would be used to, write programs. I mean, no, I need to sit down and think about this because there is something I had something in mind here, but I feel like I'm kind of losing track of what exactly I was trying to do because so here wait, let's open up. Oh, we don't need it here. We can do it here. So first we have the CPU. Okay, that's going to be an ESP32. Not even CPU. I shouldn't call it a CPU. I should just say kernel, right? Then we'll have a memory controller. That's another ESP32. Then we'll have an I/O controller. That's going to be another ESP32. Now, the idea is to be able to use. Actually, okay, I was about to say that maybe the storage controller should be a separate thing, but no, I can handle um, input and output and storage related stuff all within the same IO controller. There doesn't need to be a separate storage controller. Yeah, everything could be part of the IO controller itself. Now, what we need for the IO controller and memory controller, we are going to need to write systems that accept instructions, that accept and process instructions. So these are going to be their own architectures. They're constantly accepting instructions and executing them. But these are going to be relatively simpler compared to, you know, something because these are like purpose built. These are built to do a specific thing. When you're building an instruction set architecture, you're building something that is supposed to be programmable. It's supposed to be more general purpose. So that gets very complicated. With these, special purpose or not special purpose, but like, what do you, purpose built. But these purpose built firmwares, I don't think it'll be as complicated. There'll still be like challenges there. I'll definitely still have challenges, but it won't be nearly as complicated as creating a separate ISA. Okay, let's continue reading. So option A is the WebAssembly route, and option B is a basic virtual machine. Okay, let's read the basic virtual machine thing. If WebAssembly feels too heavy, you can use a classic virtual machine layout like Chip 8, an educational 1970s interpreted language, or even embed a tiny Lua or MicroPython interpreter. Your kernel reads the script bytecode from your memory controller and interprets it line by line. Okay. Well, the thing is, what did I want to do here? I feel like I'm losing track of because I feel like I'm mixing two ideas together. On one hand, there was the idea that I wanted to build something similar to computer hardware and a kernel running on the hardware, right? But then that requires a custom architecture, which is where things get a bit complicated. It's going to get complicated if I try to write my own instruction set architecture. So I don't want to do that. However, what I could do, oh, wait, no, sorry. So the two things that I was confusing is one is, having to build a separate computer architecture which can then be, or having to build a separate processor architecture which can then be programmed, or at the very least I can like write program. I didn't think about how I'm going to be writing the programs to run on the CPU, so it might get a bit complicated there. Would I be able to? I don't know, dude. I don't want to have to do that. I don't want to have to, first of all, create my own architecture. And then because I don't want to be writing, complex programs in assembly, then I'm going to have to create my own compiler to compile Rust code because, of course, I'm going to be using Rust. I'm going to have to find a way to compile my Rust code to my architecture. And that is all going to get very complicated, very fast. And it's also going to make me spend a lot of time doing something completely different from what I intended to do. So I don't want to do that. That is one thing, right? Um, Another thing is I could, or the other thing that I was confusing that with is running a pre-built program. So a program that I've built and compiled, running it on the running it on a kernel. So I'm basically just programming a kernel that has a shell, quote unquote a shell, and I'm writing all the programs myself, all the programs that are going to be loaded into this. I'm writing all of that myself, right? All of that is going to be part of the functionality. So there would be, let's say, an interpreter and or a shell of some sort. Within that shell, you type a command and a program executes, right? And then the modular part of that would be the RAM and the storage. So I think I want to go with the latter idea. My first idea, let me write this down. First idea was um, custom CPU ISA ESP32, right? And then we would have a memory controller ESP32, and then also IO controller ESP32, right? The problem with this is that this would require custom ISA, um, custom compiler for assembly to, sorry, for Rust to assembly, Rust to, in fact, custom assembly, right? And then probably other complications. Oh, sorry. Then we would also require a kernel, right? So all of that becomes very complicated. Here, the second idea is I'll just build a kernel plus a shell. Um, we're going to have pre-made programs. User runs programs through a shell, um, modular using various controllers. I like this idea more because this seems more doable and it's going to require much less um, in terms of, having to design my own separate architectures. I like this idea a lot more. Yeah, yeah, I like this idea. So there can be a shell. We can have an IO controller. We can have a display control. Though within the IO controller, we would be um, handling input, output, which would be display. Input would be, oh, guys, okay, I need to end the stream. That's going to be it for today. I hope you guys have a nice day, and I'll see you all next time. Peace.